Thanks, Kiran. Good morning, everybody. So, this tutorial is by the three of us. I'm Supratik, Kuldeep is here, and Moshe. All three of us have been working on this and we prepared this tutorial together. Fortunately, Moshe couldn't attend today's session, so Kuldeep and I will be presenting the tutorial. So right at the beginning, I'd like to say that we've sort of divided the tutorial into two parts. So I will be talking about the first part, and at the end of it, after my part, we'd like to have a short few minutes break, maybe where I can answer some questions that you might have about the first part, and then Kuldeep will take over. He will talk about the second. Okay. So we're going to talk about discrete sampling and integration in high-dimensional spaces, and I mean this is really a very broad area, and it's not really possible to cover everything, to talk about all the different techniques that are available for these problems. But we'll try to at least give some perspective on why this problem is important, what some of the techniques that people have used in the past, and we will focus in particular on a particular class of techniques that has been very promising in the last few years, and we'll talk in much more detail about that. Okay, so here's the problem definition. Suppose you have n variables, x1 to xn, each coming from some finite discrete domain, E1 to En, and I have a constraint, often given as a logical formula, f over these variables. In addition, suppose I'm given a weight function which assigns a non-negative real number to every possible combination of values of these variables. So given this, suppose I denote the set of all possible assignments that satisfy the constraint by this notation R sub f. So we're going to use this throughout the tutorial. So it's important to remember, when I say R sub f, it is the set of all assignments of the variables that satisfy the constraint f. So the first question that we want to ask is, can I find out the sum of all the sum of the weights of all the satisfying assignments? So when I sum W of y over all y is in Rf. And of course, if the weight is 1 for every y, then it's easy to see that we're just counting the number of solutions f. Right? And this problem is also called discrete integration or model counting. It's really some kind of summing up of weights over a constraint. And there is a sister problem, which is that we know what the set Rf is. Is it possible to randomly sample a solution from the set Rf such that the probability that the solution is sampled is proportional to its weight? And once again, if the weight is 1 for all the assignments, then you're basically asking, can we uniformly sample? And this is called discrete sampling. Right? So for purpose of this tutorial, we are going to restrict all of these domains, P1 to Pn, this is fine, to 0, 1, because since these are finite discrete domains, I can always encode them in binary, and so it will just simplify our discussion, at least for purpose of this tutorial, to consider all of the domains as 0, 1. Okay, so why do we want to study these problems? So I'm going to present one motivating application for discrete integration and similarly one motivating application for sampling both coming from very different application domains. Just to say that this problem is important in real life applications, and then we'll go into how to solve this problem. Okay, so this is standard textbook example on probabilistic inference. That suppose I have an alarm that rings. If the alarm is in a working state, either an earthquake happens or a burglary happens. Of course, the alarm would malfunction and start ringing by itself even when nothing happened. Neither earthquake nor burglary happened. And given that the alarm rang, we want to find out the likelihood that an earthquake happened. So this is the very classical instance of probabilistic inference. So we are saying that given conditional dependencies and conditional probabilities, some events of interest, and given that I've observed some evidence, what is the probability of this earthquake? So in this case, what's the probability that there was an earthquake given that the alarm rang? Okay, so and how do we solve this? Normally we basically apply Bayes' rule. So I'm sure all of you are familiar with this. So this is just the definition of conditional probability, and then the denominator can be obtained by summing up over all possible events j, and then we can obtain the joint probability of an event j and an evidence from, once again, the definition of conditional probability. So this is very straightforward textbook stuff. So how do we represent these conditional dependencies efficiently, and how do we calculate these probabilities in practice given a particular problem instance? So here is one very popular model, which once again I'm sure that a lot of you have already seen, probably most of you have seen. So these are called probabilistic graphical models. So here I have three events: burglary, earthquake, and alarm, and there are dependencies between the events. And these dependencies might be given in the following form: that here is a table of probabilities for earthquake happening, table of probabilities for burglary happening, and this is a table of conditional probabilities. Given that a burglary happened and an earthquake happened, the probability that the alarm rang is 0.3, or given that neither burglary happened nor earthquake happened, but still the alarm rang because maybe it was malfunctioning, is 0.1, and so on. So in this particular case, we have 8 entries in this table, and these are called conditional probability tables. So all very standard stuff. And how would I calculate a joint probability like this from the data that is given? So I would basically say that, well, I want to know how A and B happen together. So maybe it happens along with B, or maybe it happens without B happening. And we could just sum these two together, right? So the first subterm here is saying what is the probability that A happened and E happened and B did not happen. And this is the probability that A happened and E happened and B happened. It's just expanding from the usual definitions of conditional probability. Okay, so of course, if you have these tables and if you have the numbers in these tables, you could plug in the values there, and you could calculate the probability of alarm ringing and earthquake happening. So what we want to do is we want to see that can we visualize this problem as an instance of the discrete integration or model counting problem that I just mentioned a few minutes back, and it turns out that we can do that. So we can basically try to model in logic the dependencies that I just showed, and then we can encode the weights in certain ways, we can encode the probabilities in certain ways, and then we will see that it is possible to reduce the probabilistic inference problem to a problem of discrete integration. So I'll just quickly walk you through this simple example, how one might do it. So here we had events, alarm happening, burglary happening, earthquake happening, and so on. So what I'm going to do is I'm going to introduce a separate propositional variable for each possible outcome of the event. So this variable denotes the alarm rang, this denotes the alarm did not ring, burglary happened, burglary did not happen. Now note that in general, the alarm would have three possible states. The alarm rang or did not ring, or maybe it just rang in a very feeble way. So we could just add appropriate variables there. So the events don't have to be binary. This modeling can take care of non-binary events as well. And then I can have propositional variables which are corresponding to the conditional probability table entries. So for each entry of the table, I'm going to use a separate variable. And then I want to write a logical formula that encodes the dependencies that are represented in the table. Right? So basically, I first say that for the alarm, either it rang or it did not ring. So I have an XOR between VA and negation A. Similarly for burglary, either it happened or it did not happen. Similarly for the earthquake. And then I have these extra terms over here, extra subformulas over here, where this subformula is saying that if alarm rang and burglary happened and earthquake happened, then this variable must be set to true. Similarly, if alarm did not ring but burglary happened and earthquake happened, that variable must be set to true. And vice versa. So we'll soon see, why we are trying to do this. It will actually help us reduce the probabilistic inference problem, one of discrete integration. But this is, how I would model the dependency information stored in the probabilistic graphical model, modulo the weights, modulo the probabilities, haven't yet put them in. So this is how the basic dependencies will be modeled as a logical form. Okay, so now we've put in the probabilities. So the way we do that is we say that the weight of a burglary not happening is the probability that the burglary did not happen, which is 0.2. The weight of the variable denoting the burglary happened is the probability that the burglary happened, which is 0.8. So basically, all the independent events, in this case burglary and earthquake, will have their probabilities assigned as weights of the corresponding positive literals. Note that this is a positive literal. This is a variable denoting something. So it's not the negation of the variables, it's still a positive literal. The conditional probability table entries have one variable each, as we just showed. So we're going to assign weights of these variables to exactly the probability associated with the corresponding rows of the conditional probability table. And for everything else, I will assign a weight of 1. So all the dependent variables, all the negated literals, all of them will have a weight of 1. So this is sort of trying to put in the information about probabilities that was there in the probabilistic graphical model into the setting of this logical modeling, and then the probabilities becomes weights of different literals associated with this model. Okay. And then we will say that if you give me an assignment, maybe V of A is 1, V of negation A is 0, and so on. So if you give me an assignment of values to these variables, then the weight of that assignment I will calculate as the product of the weights of the literals in the assignment. Okay. So that's how I'm going to compute the weight of an assignment. So now, given this setting, what I claim is that the problem of calculating probabilities from probabilities of joint events from a probabilistic graphical model can be reduced to the problem of discrete integration. So let's see how. So here are our variables. We were interested in finding the probability of alarm and earthquake happening from the graphical model. So we had already encoded the dependency information in the graphical model using a formula, which I'm calling phi of probabilistic graphical model. Now in addition, I want to find the probability of alarm and earthquake. So I'm going to conjunct these two literals. And then I'm going to ask that for this formula F, which is saying that the events are related in a certain way as defined by this phi sub PGM, and then I'm interested in the probability of the alarm ringing happening. So what are the different ways in which this formula can be satisfied? What are the different ways in which alarm and earthquake can happen where the dependencies between events are as given by the graphical model. And here you find that for this formula, these are exactly the two different ways in which the formula can be satisfied. Of course, VA and VB has to be both true in both cases. VB is either true or V negation B is true. And remember, we had said that the XOR of these two must be true. One of them is true, the other must be false. And then we also had some relations saying that if A and B and VA and B and VB are true, then this, the variable corresponding to this entry must be true, and so on. And so there are exactly two satisfying assignments for this form. And note that they exactly correspond to the two different ways that alarm earthquake can happen, given the dependencies in the probabilistic earthquake. Right? Alarm earthquake and burglary, or alarm earthquake and no burglary. And now if I say that, let me try to calculate the weight of the satisfying assignments. So there are two satisfying assignments. Then, we have already said that we'll take the weight of the satisfying assignment to the product of the weights of the literals. So if you just do that, we get a sum of two products, and then remember how we set the value of the weights. They were basically the probabilities from the CPTs and the probabilities of the independent events. So you basically get the product, the sum of these two products of probabilities, and this is exactly the probability of alarm happening and burglary. This is exactly what we have seen earlier, what we are trying to calculate. What is the probability that earthquake happens and alarm happens? What is the probability that earthquake happens and alarm happens and burglary happens? Or earthquake and alarm happens. Okay, so I hope you can now see that if I could have real scalable techniques for doing this kind of calculation, where I'll give you a formula and then I'll weights of the different literals of the formula, and then I ask you what is the sum of weights of all the satisfying assignments of the formula. I could now use this to actually do probabilistic inference. And one of the nice things about this is that if I can come up with techniques which give me strong guarantees about how much precisely I can calculate this weight, then it also translates to very strong guarantees on how precisely I can calculate probabilities from a probabilistic earthquake. And I think that's an important point, because the later part of the tutorial will worry a lot about what kind of approximation guarantees can we give when we are trying to compute the weight of satisfying assignments, and these directly translate to approximation guarantees on probabilities if I'm doing probabilistic inferences. Okay, so that was some motivation for doing discrete integration. Basically, we took the probabilistic inference problem and mapped it to what is also called weighted model counting. There were weights here. And then some recent work last year, we showed that summing up the weights of satisfying assignments can also be reduced to just counting the satisfying assignments in an appropriately modified formula. So this is called unweighted model counting. So basically, probabilistic inference can be reduced to unweighted model counting through a sequence of reductions. This reduction was way back in 1996 by Roth. This we came up with last year, and this reduction is polynomial in the number of bits that are used to represent the single matrix. Okay? So basically, if you can solve this problem well, then and with strong guarantees, then you can also solve probabilistic inference with strong guarantees. Okay, now what about sampling? Now, of course, for sampling there are lots of applications. I'm going to talk about an application which comes from a very different domain, just to show that these are applications across domains. So I'm going to talk about what is called functional verification. So basically, suppose you're given some circuit or you're given a piece of code, and you want to check that there are no bugs in either the circuit or the code. And typically, what the sort of the most foolproof methods of doing this are what are called formal verification, where you sort of model the circuit or the software as some kind of mathematical system, and then you try to use properties of that system. But then there are real issues of scalability. this scales up only to systems of a certain size. Beyond that, there are computational bottlenecks. So really the dominant approach used in the industry today for this is what's called dynamic verification. So dynamic verification, what we do, we take the design, either hardware design or software design, and we just simulate it with a lot of test vectors which represent different kinds of scenarios, and then we check what the results of the simulation are and are the same as what we intended. The question now is, how do we generate the test vectors? In particular, if the test input space is very large, suppose I have a 64-bit binary operator somewhere inside my program or inside my circuit, then in order to test whether that operator is really implemented correctly in the implementation, I have to provide all possible combinations of two inputs, each are 64 bits wide. But then this is really not practically feasible. 2 raised to 120 is a very large number. So what people do, they say, okay, maybe here is some module which I don't know what it's fully doing, and it has these two 64-bit inputs, it gives me 64-bit output when I simulate it, and I would like to throw some test vectors at its inputs and then check whether the output matches what it should be. So typically what designers would do, what test engineers would do, is that they would go and ask different kinds of people who have some stake in this design, maybe the designers, people who have used this design in the past, people who want to use this design in the future, that what corners of the input space do you really care about? What corners of the input space do you think that there could be a problem? And each one of them might come up with some description of what corner of the input space they care about, and this we have written it here in a particular notation. So I just read out the first line. This is saying that if you take the input A and then if you do a 64-bit addition with the result of multiplying 11 with B using some 32-bit addition. Okay. So this is a 32-bit multiplication. So this is 64-bit addition with a 32-bit multiplication. Then the result should be 12. And these are the values of A and B which satisfy this constraint here. Or somebody might say that as long as A as a 64-bit quantity is less than B right shifted by 4 bits, that's the count that I care about. So typically, people who are either designing these blocks or who are using these blocks, they would come up with hundreds of such conditions. So these are the cases that I care about. And then what you want to do is you want to take all of these and you say that, well, let's solve all of these constraints together. These are just constraints in some logical system. Let's solve all of them together, and whatever solutions we get from there, those will be our test vectors because those satisfy all of the requirements that the designers and users give. And how do you solve these? This is basically a constraint solving system, and if you're looking at a real hardware chip or some real software system, there would be very large numbers of these constraints, and you want to still go ahead and solve them in a reasonable amount of time. So we know that SAT SMT solvers, this propositional satisfiability and satisfiability modeling theories, these have been tremendous advances in the past couple of decades, and they can really solve large systems of constraints like this in a reasonable amount of time. However, the sophistication of these solvers has also made them very difficult to predict how they will behave. Right? In particular, the efficiency of these solvers stems from automatically biasing the search for a solution towards some corners of the solution space. You give a problem and it automatically tries to figure out that in this corner of the solution space, maybe there is more likely to get a solution, and it tries to bias the search there. So if I give the system of constraints to such a sophisticated solver, it will not give me unbiased solutions. It will give me biased solutions. And these biases are based on the heuristics and all of the optimizations that are implemented inside the solver. And one cannot say, let's throw all of them out of the window because the efficiency of the solver depends on these things. Right? So this is a catch-22 situation. So what we want to do is we want to say, well, we still want to leverage the solvers, but we would not like to have any further bias when I'm choosing solutions with these constraints. We would like to sample from solutions uniformly, or I as a user should tell how the solution should be biased, not the solver. The solver should not be doing something internal which I don't have any control. Okay, so this is the setting. Basically, we have a set of constraints, and from there we can come up with a formula, which solutions of which denote test cases of interest, and then we want to sample from this space of solutions, from the space of test cases, uniformly at random or according to some bias given by the user. That's not according to the bias that is determined by the sample. And so this gives rise to this problem of generating SAT witnesses or sampling witnesses of constraints in a scalable way, because this also has to be done for large systems of constraints to be used. So if we are okay with this, so I have now given you two motivating examples from two very different domains, one for sampling, one for integration. And indeed, there are many, many more applications from very diverse areas. Simulations in physics, economics, network reliability estimation, and it's a very long list. And while these two problems might look like two different problems, in one case I'm trying to count the number of models, in the other case I'm trying to sample the models, it turns out that they're very closely related, and we will look at that connection briefly in a few minutes. And in particular, insights into solving one efficiently and approximately often leads to good algorithms for the other problem. Okay, so this is what we will do now with the next 20 minutes, 25 minutes. We're first going to look at that. Now we know what these two problems are. Now we've seen some motivations for them. How hard is it to really solve this? Computational complexity-wise, how hard is it? And then we'll see some early work on counting and sampling. We'll see some of the limitations as well. And then we'll come to a particular genre of techniques that use what is called universal hashing. So I'll describe briefly what universal hashing is. And then I'll give a brief overview of algorithms for sampling and counting using universal hashing. These are the most promising algorithms in this area today. There's been a flurry of papers in the last few years. And then the second part of the talk, Kuldeep is going to take you into a much deeper dive universal hashing-based algorithms for these two problems. Okay, so how hard is it to count or sample? So of course, if I could enumerate all the solutions by some magical means, then it would be very straightforward. Right? But then we're talking of constraints, probably millions or trillions of solutions. So it's not possible to enumerate them. Right? So let's try to understand computational complexity theory-wise how hard it is problem. So that will tell us whether there is hope for us to solve it efficiently, or must we accept approximations and use it. So exact unweighted counting so this is in fact the canonical Sharpe complete problem. Leslie Valiant showed it in 1978. Now, Sharpe complete already means that it's above the polynomial hierarchy, so it's not going to be very easy to solve this problem exactly. So this sort of sends us a warning message that when you're trying to solve this exactly, you have to incur heavy computational cost. And this is not because we are not being smart, it's just because there's fundamental computational complexity in the problem. Okay. So we could also try approximate counting, and here what we mean by approximate counting, it's not good enough to just say, here I have a count and I know it's close enough to the real count, but I don't know how close is it. I know somewhere it's close. That's not good enough. So here what we want is, we want approximate in a very precise sense. So for example, if I'm trying to do a deterministic approximation, then I would like to have an algorithm which takes the formula f, and it takes a tolerance parameter epsilon, and it returns me a number, which is the deterministic estimate given at epsilon, which must lie between the actual model count divided by 1 plus epsilon and the actual model count multiplied by 1 plus epsilon for every epsilon greater than epsilon. This means that I want an algorithm which should take the tolerance in the approximation that I'm going to do as a parameter, and it should give me a result which is within the tolerance of the exact result. The exact result is the cardinality of RF, if I'm talking about unweighted counting, and I want the result that I'm getting from this algorithm within its tolerance. So of course, the runtime is going to depend on what epsilon is, and Stockmere in 1983 he showed that there is a polynomial time deterministic Turing machine which accesses a sigma p2 oracle, which is the second level of the polynomial hierarchy. It's an oracle for a problem at that level of the polynomial hierarchy, which can solve this problem. And when I say polynomial time, it's polynomial in the size of the formula and to the inverse of epsilon. So as you make epsilon smaller, as you demand that it should be more and more precise, you have to spend more time on it. So for a particular application, if a given epsilon works for you, you may be able to get a bit easy. Okay, what about randomized algorithms for it? So here the situation becomes far more interesting, and in fact in the same paper of Stockmere, which was further elaborated upon by Jirambali and Gazarani, 1986, they showed that there is a polynomial time probabilistic Turing machine which needs access to just an NP oracle, not an oracle for a problem at the second level of the polynomial hierarchy, but needs access to just the NP oracle and which can solve this problem. And what does it mean to have a randomized algorithm to solve approximate counting? This is what it means, that my randomized algorithm should take the formula, should take a tolerance parameter, and it should take a confidence parameter. And it should return me a count which lies within the specified tolerance of the actual count with very high confidence. So the probability that, remember this is a randomized algorithm, so it is not going to return you the same result every time you invoke it. There is a probability distribution of the results that it's going to give you. So the probability that the result that it returns lies within a tolerance of epsilon of the real value is as high as you want to be. Right? But of course, delta and epsilon are parameters to this algorithm. So if you want to reduce epsilon and if you want to reduce delta, then you run it times. And here, this polytime is polynomial in the size of f, 1 over epsilon, and log 1 over delta. So as epsilon and delta reduce, the times increase. And this class of algorithms are also called probably approximately correct, packed algorithms. And this is indeed a very useful class in practice. For a practical problem, it may not be necessary to get the count exactly, to get the probabilities exactly, but to know that the probabilities are within a certain tolerance, and as long as we compute that with very high confidence, that might be enough. Okay, so what about the weighted versions of counting? So it was shown by Roth in 1996 that exact weighted counting lies in the same complexity class as exact unweighted counting, and it follows that approximate weighted counting is also the same class as approximate unweighted. Okay, so all of this is saying that the solving the problem exactly is going to be difficult. So it might be worthwhile trying to solve it approximately, and indeed there are at least theoretically, we know in what complexity classes they lie. Now it's a different matter. Can develop practical algorithms which still deliver those guarantees, and that's going to be the real focus of Kuldeep's part of the talk. Will show that it can indeed achieve these guarantees in practice while scaling up to constraints with hundreds of thousands of units. Okay, what about sampling? So there was this very interesting paper in 2000 by Bellari, Goldrick, and Mithram, which showed that you can actually achieve uniform sampling by polynomial time probabilistic Turing machine, once again accessing an NP oracle. And what does it mean that I can do uniform sampling? It which means if I take the formula and give it to my algorithm, which is going to uniformly sample for the solutions, then the probability that it generates any particular solution is independent of the solution. So as long as y is the solution of f, the probability that y is going to get generated will be some positive quantity which is independent of the solution. So that's why it's uniform. And of course, if y is not the solution, then it will never be generated. So this is uniform sampling. There is no bias towards or against any particular solution. And we also have almost uniform sampling, where we say that if I give a formula f and a tolerance parameter epsilon, then the probability that a particular solution of that formula is generated may not be exactly the same as the probability that another solution is generated, but that these two probabilities cannot differ by that much. It cannot be the case that one solution is generated with much higher probability than the other. So the probability that any arbitrary solution is generated lies within a tolerance of epsilon from the same number c, where c is independent of the solution. So this just says that you take two different solutions of f, they're going to be generated with almost the same probability, but may not be exactly the same. The previous one said that it would be exactly the same probability. Here it said that there's a little tolerance in the probability. And the tolerance parameter is part of the algorithm. And so this polynomial time is once again polynomial in the size of f and 1 over epsilon. Okay? And once again, these are probabilistic algorithms. So we require that the probability of the algorithm output some solution if the given input formula is satisfied, should be at least half, so that you can amplify it by running multiple times. So this is where computational complexity wise things lie. Very nice theoretical work done by around the year 2000. But then, what about the practice? These translated algorithms in practice. Well, so people have tried to come up with tools and algorithms for solving these problems, and I'll briefly overview a few of those, and I'll also tell you what are the problems with those. So the early exact counters, the early attempts to count the number of solutions of a formula in an exact way, were basically based on this BPLL and Davis-Putnam search technique. So basically, you do a branching search and you keep assigning truth values, and you see what other truth values of variables are implied and all of that. This is the standard BPLL-based search for finding solutions to a propositional formula. Except that what you do here is that once you find that a branch is satisfied, whatever assignments you've made so far satisfies the entire formula, regardless of the assignments you're going to make to the remaining variables, then you can basically skip the assignments to the remaining variables and just count how many assignments to the remaining variables have. So if t out of n variables have been assigned, then you know that for all, and if you already know that the branch is satisfied, then you know that for all 2 raised to n minus t assignments to the remaining variables, the branch will be satisfied. So this is a fairly simple idea. It requires some special data structures to check if all clauses are satisfied by a given partial assignment. Interestingly, this kind of data structure is not present in modern SAT solvers, and in fact, it is not present in modern SAT solvers because it's known to add to the computational overhead. So modern SAT solvers will not do this kind of check that whether a partial assignment satisfies all the clauses. They will keep on assigning values to literals, and if they can assign values to all literals without any conflict, they know that the formula is satisfied. A nice feature of this kind of counters is that you can stop it at any point of time, and whatever count it has obtained so far is really a lower bound than the actual count, because it's just exploring the search tree, and whatever part of the tree it has explored, it's got some count from there, it's certainly a lower bound. Then there are people who have worked on exact counters. RelSat is a very well known exact model counter for this problem. So what is done here is that you take the formula f and then you construct what is called a constraint graph out of it, where the variables in the f are the vertices, and you draw an edge between two vertices. Both these variables are present in some clause. Typically, the formula f would be taken in conjunctive normal form, so you have a set of clauses, and as long as two variables that appear in the same clause, you connect the line edge in this graph. And then you find out disjoint components of this graph, which means sets of variables which appear together in some clauses, but then if I take another disjoint component, that's another set of variables, none of which appears in any clause with the variables of another component. So if I look at two disjoint components, it means no vertex here is connected with any vertex here, which means none of the variables here appear in any clause. So this actually leads to a decomposition of the original formula itself into a set of sub-formulas, and the original formula is given in conjunctive normal form. It's decomposed into a conjunction of sub-formulas with disjoint supports. And once you do that, once you have a conjunction of formulas with disjoint supports, you can count the models of each one of them and this multiply. So that's the optimization that's used, and then there are a whole bunch of heuristic optimizations. Then, there are even more interesting things that have been done, and this has given rise to sort of most of the state-of-the-art exact model counters will be using this thing called caching. So essentially, this is saying that if in two different branches of the search tree you end up encountering the same subformula, if you've already counted the number of solutions of this subformula, why redo it? Just remember it somehow and reuse it. So it requires remembering some kind of signature of a satisfiable subformula component, and then there are different ways in which the signature is stored, and it's cached basically, and once there's a caching, you can reuse the result. And this has also been used in the weighted context, where as you are doing a PPLL search, not only are you just counting the number of solutions, you're adding up the weights of the solutions also. And there is a class of tools which actually do exact counting using this thing. So it's a DPLL search based on finding components and then caching subformulas and caching components. And it starts getting more and more complicated. There is another line of work where what has been done is you take a formula and you compile it into another form such that it is easy to count the number of models from that new form. And what do we mean by easy? It means in polynomial in the representation of the new form. In time polynomial in the representation of the new form, you calculate the number of models. And here there are several dominant representations that are used. Reduced order binary decision diagrams. This proposed way back in 1986. The problem is that building this representation itself might be expensive. Once you build this representation, then it's easy to count. Then there are also more recent things like deterministic decomposable negation normal form. This is really a negation normal form with some following additional properties, that whenever you have an AND operator, then you know that all the arguments of the AND will disjoint supports, and whenever you have an OR operator, then all the arguments will disjoint solutions. So this allows you to count the solutions a little bit more efficiently. And more recently, there have been other representations called sentential decision diagrams, and several papers based on those, which also make it easier to count once you've compiled the formula in this form. So how far do exact counters go? So they work reasonably well in small to medium-sized problems, and also in some large problem instances when there's some special structures. And what our experience has been that they're not bad at all if it suits a particular application. So whenever possible, you can use them. But as you try scaling up, sharp completeness is going to hit you eventually, and you're going to suffer from scaling. Okay? So there are some other classes of counters that people have used. These are called bounding counters. So these are interesting class of counters. They say that, well, I'll give you a number and I'll tell you whether it's an upper bound or a lower bound, but I can't tell you how far off it is from the real count. So there are no approximation guarantees, they're just bounding guarantees. So well, these people have used in some kinds of applications, but I guess not having approximation guarantees doesn't really much. Markov chain Monte Carlo techniques are of course very popular, they are very well studied. They have been used a lot in sampling and counting, metropolis testing, simulated handling, a lot of intense studies have been done on these. The high level idea is, at a very high level, is that you start from a state or an assignment of variables, and then you choose your next state using some local biasing functions, and then you repeat this for an appropriately large number of steps, and after you have repeated this for a very large number of steps, then the samples follow a target distribution. So the problem here is that the convergence to the desired target distribution is guaranteed only after a very large number of steps, and this n is often so large that in practice people don't go up to n, they truncate it earlier, but once you do that, the guarantees go up to 2, and there has been some empirical work done to show that there are really very weak guarantees once you do heuristic truncating of the number of steps. Okay, so this brings me to the real focus of the remainder of the tutorial, which is going to be sampling and counting based on techniques related to hashing. And these have been extremely successful in recent years. A lot of papers are published, and that's what we're going to look at for the remainder of the tutorial. So very quickly, what are hash functions? So they are mappings from a typically large domain to a much smaller range. In our context, our domain is the space of all possible assignments. So 0, 1 raised to n, where n is the number of variables in our formula, that is the domain. And we want to map it to a smaller range, 0, 1 raised to n, where n is less than n. Right? So these we will call as assignments, and whatever the assignments are getting mapped to, we call the cells. So pictorially it looks like this. We're going to see this picture a lot of times in the remainder of the tutorial. So if this big oval represents the set of all possible assignments to the variables, the black dots there, black and yellow dots, they represent assignments that satisfy f, and these partitions here represent the different cells that are generated by a given hash function. Right? So a hash function basically takes a bunch of assignments, maps them to a particular cell. So this is the pictorial view of what a hash function is. Okay. So good deterministic hash function would be something that if the inputs were distributed uniformly, then it would keep roughly equal number of inputs, equal number of the points, equal number of the assignments in each of the cells. But then, we are talking about solutions of systems of constraints, and we do not know a priori if solutions of systems of constraints are distributed nicely in the solution space. We do not know that. And so, deterministic hash functions, finding deterministic hash functions which will sort of ensure that the solutions are distributed nicely among different cells is an almost impossible situation unless the constraint is very, very special. So what we use instead is this class of hash functions called universal hash functions, which was originally proposed by Carter and Bregman in 1977, used by Simpson to solve hard combinatorial problems in 1983. So what are universal hash functions? So instead of coming up with one hash function, we define an entire family of hash functions, let's call them capital H, with some properties. Each hash function in H takes me from the same domain to the same range, but all of them are different. And then I'm going to randomly choose one hash function from this class. Completely randomly choose one hash function from this class. And now it can be shown that it doesn't matter how your solutions were distributed, how your inputs were distributed. For every distribution of inputs, all cells are going to be roughly same. roughly similar looking in the sense of expectation. Right? Basically, you're saying that since I'm not going to have one kind of hash function, I'm going to randomize the way in which I'm partitioning the space. So it doesn't matter how your solutions are distributed. The probability that the cells are going to get roughly even distributions of solutions is high enough. So it guarantees probabilistic properties of cell sizes even without knowing the distributions of the solutions. And this is a very important point. And this was used by Simpson very effectively in 1983 for combinatorial optimization. Stockmeyer's papers, which showed the computational complexity of approximate counting, also uses this in a very crucial way. So I just want to spend a slide on how this looks like. So we are going from 0,1 raised to n to 0,1 raised to m, and then I want to have another parameter for these universal hash functions called r. So we call these r universal hash functions from 0,1 raised to n to 0,1 raised to m. So this should have been for all x in 0,1 raised to n, alpha n 0,1 raised to n. So this is just saying that you take any assignment in your domain and you take any cell in the range, and the probability that your randomly chosen hash function maps that assignment to that domain, or any assignment in any domain, is the same. It's 1 over 2 raised to n. So this is uniformity. 2 raised to n is the total number of cells in the range. So any assignment gets mapped to any cell equally probably. And the second is about independence, which says that if you take r different assignments and if you take r cells, may or may not be the same, and then what is the probability that the first assignment got mapped to the first cell, the second cell, and the rth cell, and this is going to be exactly the product of the probability of the first got mapped to the first cell and the second got mapped to the second cell. Right? So it's going to be the product of the probabilities, which is basically where you get this independence differentiation. And R-wise independent basically corresponds to R universal hash functions. R universal hash functions means you can get this R-wise independence. So that is, and the higher the R is, the stronger guarantees you get in the sizes of the cells, the lower probability. And basically the cells are going to look almost similar to an expected sense. The variation, the variance of their sizes are lower, the higher this degree of independence that you choose. So this is very nice, but then how does one get these R-wise R universal hash functions? So it has been shown in the literature that they can be obtained by using polynomials of degree R minus 1 in some really large Galois field. Okay. And if I'm talking about number of variables, let's say 10,000, and if I want 10,000 independent hash functions there, doing arithmetic in Galois field of size 2 raised to 10,000 is not fun. This is very, very difficult. So if I keep R low, then I get lower complexity of reasoning, but then does it suffice? Is it good enough? And it turns out that if I have R as low as 2, so 2 universal hashing, there's a very simple class of hash functions which satisfy this property of universal hashing, and they also give us fairly nice properties as far as our requirements are concerned. So what is this class of hash functions? You take these variables, and then I want to get a mapping from 0,1 raised to n to 0,1 raised to m. So what I'm going to do is I'm going to repeat m times the following step. I'm going to take every variable with probability half, XOR them, and then add 1 with probability half. So for example, 1 got picked, 2 didn't get picked, 3 got picked, 4, 5 didn't get picked. So whatever variables got picked, I'm just going to XOR them. And then at the end, I'm going to add 1 with probability half. So in this case, I did not choose a 1, so it got XOR with 0, which means it's the same. Otherwise, it will get XOR with 1. And if you do this m times, right? So if you repeat this process m times, then you can see that every assignment in 0,1 raised to n basically gets mapped to a vector in 0, 1 raised to n, because each of these is taking assignment, XORing some randomly chosen bits there, and giving you one bit, either 0 or 1. So if you do this n times, you get a mapping from 0, 1 raised to n, 0, 1 raised to n, and that's the hash function that we're going to use. So if I want to say what are the assignments in a particular cell, let us say the cell denoted by whatever 0, 1, 0, 0, 1 over here. So this corresponds to a cell. So what are the assignments corresponding to this cell? I have to say, okay, take the original formula and add these constraints, that this XOR gives 0, this XOR gives 1, this XOR gives 0, and so on. And all the satisfying assignments of this will be solutions of F that lie in the cell that I am choosing. Because the cell that I am choosing is defined exactly this way. M times you pick variables with probability half, XOR them, and set them to 0 or 1. Okay, this has some very nice properties. So this is as simple as that, as far as implementing is concerned, has very nice properties. In particular, this property Kuldeep is going to use, where say that suppose the number of solutions in an arbitrarily chosen cell is some random variable x. So what is the mean and variance of the number of solutions in the cell? Ideally, we would like all the cells to have almost equal number of solutions. Right? That was the whole purpose of partitioning using these random hash functions. And then, so what is the expected number of solutions in a cell, and how much can it deviate from that expected number? And if I define an indicator variable which says that for an assignment it is 1 if it is in the cell and it is 0 otherwise, then the number of solutions in the cell is just the sum of these indicator variables. And the pairwise independence, remember these are two universal hash functions, the XORs are two universal hash functions. The pairwise independence makes these indicator variables pairwise independent. And now we can show that the expected number of solutions in a cell is exactly the total number of solutions divided by the number of cells. That part is not hard, but this comes from the random choice of the hash function. But this is the more interesting part, that the variance of the number of solutions in a cell cannot be too high. And this comes from the two universal hash function. So these two taken together is saying that, well, we roughly have same number of solutions per cell. The expected number is exactly right, and the variance is small. So they look more or less the same if we could use this universal hash functions. And this is the crucial fact that Kuldeep is going to describe. Right? And so this gives us very nice concentration bound. So I can now say that the probability that this number of solutions in a cell lies within a tolerance epsilon of the expected value is something like this. And if I want to convert this to something like 1 minus 1 over k, all I need to ensure is that I have to choose epsilon appropriately. Right? Some simple math there. And this was used as early as 2000 by Mitra for generating solutions of Sand witnesses in a uniform way. But what they did is they employed n universal hash functions instead of 2 universal. And while this works well for small values of n, our experiment showed maybe up to 30 works. But for high dimensions, we operate in a large Gaussian field. And so exactly this is what their algorithm does. It takes the space, partitions it up into smaller partitions, using into smaller cells, using n universal hash functions. And for the right choice of partitions, the number of solutions in each cell is small enough, it's not very large. So you basically keep partitioning until the number of solutions is small enough. And then you check if all the cells are small, so that's your empty query. And if so, you pick a cell randomly and you pick a solution randomly. So this is the algorithm by Mitra. This query that we need to do, figure out whether all the cells have become small enough, turns out very hard to do if you're using n universal hash functions, which involves elements of the Galois field in a very large Galois field of very large order. Now I mentioned at the beginning itself that these two problems are sampling and counting are kind of interrelated, and Jerubali and Vazirani actually formalized this very precisely, saying that there's a polynomial reduction between them. And so that's a very nice result in theory, but it did not translate to anything useful in practice. First of all, because we neither had a good algorithm for almost uniform generation nor for back counting, but we knew that if we got one, we get the other, but we had neither. And then the reduction here, although it's polynomial, is actually not very efficient in practice, particularly when we're dealing with very high dimensional spaces. Like n is a million or 100,000, then these reductions are not efficient. So just to put things in perspective, this is where, this is the scale for how strong guarantees to existing method scale and what is their performance. Then we have this Villani-Goldberg-Kittrang and other exact techniques which give very strong guarantees, very weak on performance. Markov chain Monte Carlo, strong on performance. I could also take SAT solvers and try to randomly bias them. They're good in performance, but their guarantees are very poor. So we would like to fill this gap in between, and that is where XOR, two universal hash functions come. So I've just shown you XOR-based hash functions. It turns out that these have been used for quite some time in the literature, and most interestingly, in a series of papers recently, Stefano Arman, I don't know if he's here, he and his group, and also the participants, they use this to show, to solve different variants of the counting and sampling problem. So this is just one of the interesting work that we did, where we combined XOR with maximum a posteriori probability calculation as well. So it's just to say that there's an entire flurry of work using XOR-based hash functions recently. So in the remainder of the tutorial, I've already overshot my time significantly. The remainder of the tutorial, Kuldeep is going to take you into a deeper dive in this. We've been working in this area for more than 3 years now. A whole bunch of papers that have in this, but Kuldeep is going to give you a very brief overview of what we're doing. So,
I missed something. Maybe I missed something. What is the advantage of going to the cells, then working with the cells after the hashing? Why don't you just take a random sample from the original?
But then it would not be randomly distributed over the solutions. It would be randomly distributed over the space of all assignments. But I want to randomly sample from the space of solutions. Right? So, I mean, in your entire space of assignments, the solutions might be in one corner. So, if you just randomly sample from the space of assignments, you're not going to reach there. So, what we do is we just partition it randomly. We take the entire space and partition it randomly, such that all the cells now have roughly the same number of solutions. And then I pick a cell randomly and then I
Other questions?
You can take the questions because I overshot my time a little bit.
Yeah.
So I'll just.
Yeah, sure.
Okay, so I'll be now talking about hashing-based approaches, how exactly most of the techniques that have been proposed over the years by a lot of people, how they work. So for this part of the tutorial, I'll first discuss how hashing-based approaches for integration work, then taking these approaches to sampling, and one of the important problems that has generated a lot of interest in the community is how do you design efficient hash functions. So to start with, just to recap, discrete integration is same as counting or in some space where you have a set of constraints. In this case, we will be concentrating on the Boolean case where the domain is 0, 1. So if you have n variables, we are talking about 2 to n possible assignments. We have some set of constraints. We again denoting that by F, and RF is the set of all the solutions of F. And the problem is, how do we estimate the number of solutions? So which is estimating the cardinality of RF. So if we assume this oval to be the space of all possible assignments, of course this is not how the hypercube for 2 to n looks like, just a simple pictorial representation. And if every dot is a solution to the set of constraints, and the problem we are now interested is counting the number of dots. So one way could have been, well, let's just count one by one, but that's not going to work. That is very hard problem. Enumerating is not going to work. So in that case, what Supratik discussed, the idea can be, what if I could partition the space of all solutions into cells that are roughly equal and small enough that you could actually count in one of the cell. Remember, earlier we started with the whole thing being just one cell. There the number of solutions was way too large, so we would not be able to count. The number of solutions could actually be exponential. But if we can do such a partitioning, then all we had to do is just go and pick one random cell. We know that the number of solutions in every cell is small, so we can actually count all the solutions in a cell, and our estimate will be the number of solutions in this cell multiplied with the total number of cells. The important question that comes is, well, how are we going to partition this into roughly equal small sets of solutions without drawing the distribution? And this is exactly where we use two universal hash functions. So, Supratik discussed that the use of two universal hash functions allow us to theoretically prove that without making any assumption on the distribution of solutions, such a division is possible and can be done efficiently. There are three important questions. Once we agree that we will be using the two universal hash function, the first is, how large are these small cells? How do we quantify exactly what is a small cell? Second is, how are we going to compute solutions in a cell? How exactly it is going to look like going to one cell and computing all the solutions in that cell? And the third is, how many cells do we want to partition into? So for the first question, how large these cells should be? Well, we don't want them to be too large. Otherwise, originally we had one cell and we could have treated the problem just counting all the solutions in that one cell, because the number of solutions can be exponential. Also, using classical sampling results, you can show that we cannot have them to be too small. Otherwise, the ratio of variance to the mean becomes very high. When a cell can have only 0 or 1 solution, then the variance can be very high. So the dependence is 1 by epsilon square with respect to where epsilon is the tolerance, how close count we want. So we quantify this by pivot. We say that a cell is small if the number of solutions in the cell are close to the pivot, and the value of pivot comes to be 1 by epsilon square. Second question, how are we going to solve the compute solutions in one cell? To do this, just to recap how we construct these hash functions, we have a set of variables x1 to xn. We are constructing hash function by putting m random XORs. Every XOR we construct by picking a variable with probability half. This very seemingly simple construction actually works. And then what we get is, once we have this set of m random XORs conjuncted with the original formula, that is exactly the cell we are interested in. So we give this set of constraints to a set solver, and or to other combinatorial solvers if you would like. And solving a cell just means asking a solver to give us a solution for this set of constraints. So you have the original formula F, and you have these m random XORs, and you give all of these. This can be represented very efficiently in various formats for solving, and we give this to a solver, and we ask, give us a solution for this set of constraints. If you want to go beyond just getting one solution, we get a solution, we say that, give me another one, not this one that you just returned. And such a procedure would work if you are interested in enumerating only small number of solutions. So this is where it is important that we do not get into an algorithm where we have to enumerate too many solutions. So we would like to enumerate only a few small number of solutions. Only then this idea would work well. So the third question is, how many cells? So the whole time we have been talking that we want to partition so that all the cells have roughly pivot number of solutions. In some sense, if we want to partition to 2 raised to n star number of cells, this is how it should look like. If RF is the total number of solutions, the total number of cells should be RF divided by pivot. That does look like catch-22 because we are interested in getting RF, and now we want to know RF so that we can partition it into correct number of cells. To get around this, the algorithm that has been proposed, it's pretty simple at first glance. Well, we do not know how many cells we have to partition into, so we are going to sequentially check. So we want to partition into some power of 2 raised to m. And we are going to try for m equals to 0, m equals to 1, and we will go till n. And at every step, the check is you partition into 2 raised to m cells, and you pick one of the cells randomly, and you check if the number of solutions in this cell is less than pivot. If answer is no, you increment your value of it. Important thing, and we will be stopping at the first n when the number of solutions is less than pivot. One important thing to note here is, because we are dealing here with multiplying probabilities, it is very important that all of these steps are independent. This forms the crux of all the proofs, that at every step the hash function and the cell that we pick, the choice across 2 m's should be completely independent. Otherwise, when you have a set of events in the probability expressing you, in the conditional probability, you will not be able to multiply them. So the number of set calls in this case is just linear in the number of variables, because we will be checking for n from 0 to n. So in the worst case, we will be making order of n calls to the sets. So how does the algorithm look like? We start with the problem, we treat the whole problem as one cell. We ask if the number of solutions is less than pivot. If the answer is no, we partition into 2 cells, pick one of the cells randomly, ask again if the number of solutions is less than pivot. We keep doing until we reach a point where the number of solutions is indeed less than pivot. When I mentioned that the hash functions have to be independent, what it means is that over these 2 steps, the partitioning, when you are doing, you cannot use the cells in the order partition. You have to do partition of the solution space into different cells completely independent. So the key lemmas behind this technique, what we had to prove is that we will actually stop at the right value. So we wanted to stop at m star, which is log of Rf over pivot. So if 2 raised to m star is the number of cells, and if we do this linear scan, then with very high probability, we will stop very close to the right value of m star. And then the second lemma that is very crucial for algorithms that have been based on this initial idea, that if you stop close to the right value and you get an estimate at that value, your estimate is correct with high probability. So there are two steps. First, to say that this linear scan actually stops at the right point, and second, if you are at the right point, you will always get a correct answer with high probability. And this indeed allows us to give the packed, probably approximately correct guarantees that we talked earlier, where we say that approximate counting algorithm that takes the formula f, epsilon and delta gives the count which is within 1 plus epsilon factor of the exact count with confidence at least 1 minus delta. And the algorithm makes of and log of 1 by delta and 1 by epsilon square falls to the NP oracle. NP oracle for our case becomes a set solver. So we'll be making these many calls to the set solver. This is also fits perfectly in line with the prior theoretical work that we discussed by also in the line of Stockman's result, that you make log of 1 by delta, 1 by epsilon square calls, and in the size of the formula. So n is capturing the size of the formula. Here we, by n we say the number of variables, but that is of course less than the size of the formula. So how well does this work in practice? And to measure that, we compared with exact counters. So what is very interesting is that there are of course large class of problems where exact counters can really efficiently solve the problem. And then there are problems where exact counters terminate a timeout, and this is where these approximate counting algorithms work well. So for the class of problems where one can get exact count, our approach is that well, just get the exact count. There is no use of trying to get an approximate count. And then these approximate counting algorithms can indeed solve class of problems that are beyond exact counters. How good are the estimates obtained by these exact approximate counters? So this is results our subset of benchmarks that is from 2013, where for the benchmarks where you know the exact count, which you could compute using the exact counter, you run these experiments with setting epsilon to 0.75, delta to 0.1, so you would expect that your count are within 1.75 factor of the exact count with confidence at least 90%. What has been very interesting, an observation that has been observed consistently by others in the community as well, these hashing-based algorithms tend to give counts that are very, very close to the exact count. So in this case, for all the benchmarks, the count was indeed within these two bounds. It was only about 0.04 away from the exact count. And in some sense, we think that, there has been attempts to improve the proof of the hashing-based techniques, that theoretically we are not able to harness the full potential of the XOR-based hash functions in the proofs. But what has been interesting, and observation that has been consistent by other authors as well in different algorithms, is that the error that you get when you use these algorithms is It's very, very small compared to the theoretical guarantees. So over the last 2 years, one of the important questions was, can we reduce the number of set calls from O of n? We want to take programs with hundreds of thousands of variables. O of n is actually a big number if you have to make 100,000 calls to a set solver. And an interesting observation was this the algorithm that I just described seems to work even if we do not have independence across different hash functions. But independence has been sort of very important key to all these proofs because they use typically things like Chernoff bounds and all. Without independence, it becomes very hard to combine different events. So independence has been sort of very important across for a long time in different proof techniques. But suppose one could have hash functions to be dependent. What would that change? Well, if we could have it to be dependent, then we could start with a cell and we could do iterative refining of the cell. We could just concentrate on the one cell when we are partitioning it to. So we start with the whole problem. We partition into 2 cells, and then when we had to partition to 4 cells, we just pick the cell that we were looking at and we partition that cell into further 2 cells. So what that allows is to have the number of solutions will become monotonically non-increasing with n. Since you are focusing on one part and you are iteratively partitioning the same cell, at no point the number of solutions can increase. Suppose if the hash functions could be dependent, and if we have the similar algorithm where we had to stop at the first value of n, when the number of solutions is less than given. If we have monotonicity, we can actually do the search in any order because that point is unique. We can actually just do a binary search. And one of the interesting development has been to prove that yes, hash function can actually be dependent. So why, and this required proof techniques which were completely different from the prior attempts based on hashing, is because the independence allows us to escape from a bad scenario, which is suppose we make a bad choice earlier. When we are partitioning, we choose a cell that was bad. The next step we have a way of getting out because it is independent. But in this case, we'll be stuck with the bad part of the space, since we are going to be iteratively refining that one part of the space. The key idea in the proof has been that the probability of making such a bad choice early on is very, very small. So while yes, if you make a bad choice, you'll be stuck with it, and probably you are going to give a wrong answer, but making a bad choice away from the right value of m star is very, very small. So this allowed the recent hashing based algorithms to take a jump where instead of making linear number of calls of n calls to NP oracle, the number of calls could be log n calls to NP oracle. And of course, the theorem statement looked very similar to what was there for approx MC. These techniques there have been recent developments to do a completely new proof structure that allows us to get of log n number of calls to NP oracle than just of n calls to NP oracle. One of the nice aspects in hashing-based approaches has been that every progress that you make theoretically actually translates in a lot of times very well to practice. So in this case, I am showing experimental results comparing approx.MC and approx.MC2. So suddenly, because we are not making linear number of calls, we are making only logarithmic number of calls, the problems that one was not able to solve even within 8 hours can now be solved within a few hundreds of seconds. So this was what I discussed on the techniques for integration, which is the same problem as counting, and the hashing-based approaches. There are more techniques, but in the interest of time, I have to stop there. Where basically the idea is you take the solution space, you partition into almost equal small cells. You pick one of the cell. You do the estimate, you compute the number of solutions in that cell, multiply it with the total number of cells. And all of this comes with theoretical guarantees of epsilon delta. Yeah. No assumptions. So we are hoping from this tutorial to explain all the progress that in the community of hashing-based design algorithms we have been making and others, to just emphasize that all of these hashing-based techniques make no assumption on this distribution of solutions, no assumption where exactly in which corner solutions are if they are randomly distributed, no such assumptions. The key is to use these universal hash functions. So now I will move on to hashing-based approaches for sampling, and I will define. I will discuss Unigen, which is our series of works, which has been one of the hashing-based approaches that promises scalability and at the same time theoretical guarantees. The key idea again is very similar. Start with all the cells, you partition so that all the cells are roughly small and also roughly equal. In that case, we pick a cell, we check if it is small. If yes, we pick a solution randomly from this cell. So remember, we will be picking a solution randomly from this cell only if it is small. So at no point we will be enumerating too many solutions. Again, three key challenges. One is how large is this small cell, how much universality we need, and what is the value of m, how many cells do we have to partition into. For the first question, the answer again comes back from classical sampling results that we give if the size is 1 by epsilon square. It is very hard to get around 1 by epsilon square bounds. For independence, there was slight interesting result that while using the results by Jerome Valent and Vazirani, 2 universalities should be sufficient, but the design of hashing-based algorithms, the proof structure actually requires 3 universal hashing. So one can say, well, let's go back to Jerome Valent Vazirani's result, and once, if we want a uniform sampler, we are just going to call approximate counter, which uses 2 universal hash functions, but that is not practically efficient. And all the design of recent practical efficient sampling algorithms requires 3 universal hash functions. One of the interesting results by Gomez et al. In 2007 was that these XOR-based hash functions are indeed 3 universal. So we do not have to change anything, it's just that we'll be still using the same hash functions. How many cells? If we go by the same logic, we want the right number of cells, and the right number of cells is again if RF is the total number of solutions and pivot is the number of solutions we want in almost every cell, the right number of cells is 2 raised to n equals to RF over pivot. So if n is log of RF by pivot, again we cannot compute the exact count, but if we have an approximation, suppose I could give an approximation to the RF, then it suffices just to concentrate on values of the number of cells close to this approximate value that is written by an approximate. So suppose I give an approximate count of RF at C, then we have to concentrate on Q minus 1, Q and Q plus 1, where Q is log of C by pivot. We ideally wanted log of RF by pivot, but if C is approximating RF, then all we have to do is concentrate around these three values of the number of cells. So what does the algorithm look like? You first go and compute the approximate count, and then you check for these three values of the number of cells. For every value, you check if the cell is small. If it is, then you pick a solution randomly from the cell, otherwise you move on to the next value, and there is a chance that in all these three cases you will actually not find a cell to be small. So that's where these algorithms are called, they have failure associated with them. So if this check, the check in line 7 fails for all the three values of I, then we say that the algorithm has failed. This is very similar to at the very start of the talk when Supratik introduced Bellaire-Gaudet-Patron. This algorithm, here also the similar thing. There is a failure probability associated with sampling algorithms. Of course, we want that these algorithms should not fail. Should fail with at most 1/2 probability. Should not fail more than 50% of the times. Otherwise, it would not be very impressive. One question one might ask is that are we back to Jerome Valent and Vazirani since we are calling the approximate counter? Answer is not really, because the reduction proposal Jerome Valent Vazirani has had to make linear number of calls to approximate counter. Here you make one call to approximate counter. And one more interesting thing is, if you typically we are not interested in just getting one or two uniform samples, we are interested in getting a lot of samples, and in this new hashing based approach, you have to make calls to approximate counting only one regardless of the number of samples. In case of Jerome Valent and Vazirani, that is not the case. So this allows these algorithms to have 1 plus epsilon bounds. Furthermore, Unisen, one can show, there have been other algorithms similar to Unisen. For Unisen, one could show that the success probability is at least 0.52. In practice, the algorithms almost always succeed. The number of calls you have to make to NP Oracle is n over epsilon square calls after you have made one call to the approximate. How will they perform? So this is comparison with XOR sample prime, which was state-of-art sampling algorithm, but did not have theoretical guarantees. And Unisen actually is 1 to 2 orders of magnitude faster than an algorithm that did not have theoretical guarantees. So one of the questions that one is typically interested in, well, it is good that you have theoretical guarantees, but how will they perform in practice? In theory, maybe no difference, but in practice, there is too much difference between theory and practice. So one way is to say how close to uniformity these algorithms are in practice. This is important because in 2007, Kitchen Goldman showed that MCMC-based algorithms, when you do the when you clip after a certain number of MCMC rounds, the distribution you get are far from uniform. So we are interested in how far these algorithms are from uniformity. So one way to measure is using statistical distance measure. I'll be showing something more pictorial here. So what one can do is take the benchmarks where the number of solutions is not too large, because then you could mimic a exact uniform solver. If the number of solutions is not too large, you could mimic a truly uniform solver. In this case, I'll be showing for one of the benchmarks where you have about 16,000 solutions, you run it 4 million times, you count how many times a solution occurs, how many times a solution is output, you then group the solution according to the number of times they appear. So we would be grouping all the solutions that appear 250 times, we will be grouping all the solutions that appear 300 times, and if you work out math, you could show that the distribution you should be getting of the frequency should be a Poisson distribution. If the underlying distribution is uniform, then it would give rise to a Poisson distribution. So what kind of distribution are we interested? Here we are interested in on x-axis we will be putting the number of solutions, on y-axis the frequency. So a point here says 228 solutions appear 250 times. So a quick check just to make sure that they are still awake. If you could differentiate between one of them is unigene and one of them is ideal uniform sampler. And this is one observation that has been consistent across a lot of experiments, but there is actually no difference between the two. In this case, it turns out that the purple is ideal sampler, yellow is unigene, but statistically the distributions are indistinguishable. So don't worry if you could not get it, because using any kind of statistical means you cannot differentiate these distributions. So what these hashing based approaches give is they allow us to get scalable counters and scalable uniform generator. And now for the last part of the talk, I will be discussing how to improve, how to design efficient hash functions. So as I discussed earlier, we use these random XOR constraints, and one of the big challenge there is how large are these constraints going to be in practice. So the number of if we pick every variable with probability half, we get n by 2 constraints, and one of the challenges has been, can we design smaller parity constraints without losing theoretical guarantees? So we want to shorten the XOR clauses but not lose theoretical guarantees. There have been a lot of approaches, so I will quickly just discuss two approaches. One has been inspired from work on error correcting codes, where one of the recent results has been that it is possible to use logarithmic size constraints, and using that you could show that the ratio of the variance to mean square is monotonically decreasing as the number of solutions increase. Unfortunately, so far there have been a lot of attempts, but what has not been able to prove is that give a slightly stronger guarantee that one would ideally want, which is to say that the variance is less than the mean. Here, all you could say is about the variance over mean square. So this leads to increase in the number of NP calls, and this is there's a lot of interest on designing hash functions where you do not incur high cost in the NP calls, and very active area of work. I think there were a couple of papers at ICM this year also. The other approach has been what we call as independent support. So there the observation is, well, not every variable is important in the formula. So if two solutions agree on a subset of variables, so if we could say that we would define something as independent support, so that if two solutions agree on these independent support, then they must be equal on the rest of the variables. So suppose we were encoding something like C is A or B, then we know the values of A and B, then we can know the value of C. And the key idea there is that we have to hash only on the independent variables. So the average size of XOR gets reduced from n by 2 to the size of independent support. So in the interest of time, let me put some slides on. And one of interesting development last year was to show that computing a minimal independent support can be reduced to a very well-known problem in programming languages community called minimal unsatisfiable subset, for which there has been a lot of tools developed. And once you compute this minimal independent support, you can plug it into the sampling and counting tools. One aspect one might ask is how hard it is to compute such a minimal unsatisfiable subset, although the complexity class is almost as hard as doing uniform generation or approximate counting, but in practice we see that it really helps to first compute the independent support and then do the sampling and counting. Typically one can get about an order of magnitude speed up. Here the red are for the original formula, original approximate counting algorithm, and the green for the one that first calls it independent support. You are typically able to get, the plots are always on log scale for this talk, so you are able to get about an order of magnitude speed. The same for uniform sampling, it gives an order of magnitude speed. So let me conclude this with some future directions. I would like to point out that there's a lot of interest, there has been a lot of work in different dimensions, and design of hash functions, efficient hash functions is very interesting right now. Here I'll be talking about one other kind of direction that has not been looked up so far is, can we take these techniques that we focus so far on Boolean domain and get to more expressive domains. So while in theory, of course, there seems to be no need unless we go to higher logic, but in practice, in recent years, what we have seen is that there has been a lot of development in the solving technologies that tend to reason at higher, richer constraints. So things like C-flex that allow you to write linear constraints, that allow you to use variables with larger domains. So if one has to harness progress in those solving engines, we have to take two steps. One of them is how do we design efficient hashing schemes. Recently, there have been some work on extending the XORs to these richer constraints, sort of generalizing them, but that gives theoretical guarantees but fails to harness the progress in the solving engines. So design of efficient hash functions for richer constraints is still very much an open area. Once we design such hash functions, we'll have to also design, probably have some sort of addendums to the algorithms to solve these hash functions efficiently. So in case of set, what I did not discuss, the focus on using XOR led to a lot of improvement in one kind of set solving, which is crypto-mini set, where the XOR constraints are given first class citizen treatment. So something similar is going to happen if we go to richer constraint domains. With that, let me conclude. In this tutorial, what we discussed sampling and integration are very fundamental problems in artificial intelligence with applications from probabilistic inference to verification. The related approaches typically suffer from one of the drawbacks. Either you get theoretical guarantees or you get scalability, but you typically lose any kind of theoretical guarantees associated with it, or you have to make very strong assumptions on the distribution. Hashing-based approaches promise guarantees as well as scalability. The important advances over the last few years in hashing-based approaches has been for discrete integration, reduction of NP calls from O of n log n to O of log n. Efficient hash functions have been proposed based on independent support. For sampling, reduction of approximate counting from O of n to O of 1, and usage of 3 universal hash functions. In practice, if you look at attempts to use these earlier hashing-based algorithms where these bottlenecks were there, you had to make too many NP calls, or you had to use higher universality. One was able to solve problems with very few, about 10 to 20 variables. And now there are tools where you can indeed solve problems with hundreds of thousands of variables. So with that, Supratik and I would like to acknowledge our collaborators who also helped in preparation of these slides. We have put software and papers that we discussed in this tutorial on the site. We will also be posting more detailed material from the comments here. So with that, I would like to conclude. Thank you everyone for listening, and I'll be happy to take questions.